I'm going to talk about membrane reactors in this screencast, and the reason is when we start looking at exothermic reactions, we ask what are the options when the reactions are limited by equilibrium. So I am showing an energy diagram for a reaction A plus B goes to C plus D. It's exothermic reaction. The activation energy for the forward reaction is here, and the activation energy for the reverse reaction is this value. As we raise the temperature, the rate of the reverse reaction increases more, and so our equilibrium conversion decreases. So increasing the temperature will not help us. Well, we can lower the temperature, and that will now favor the products. The problem is it will also lower the reaction rate. So one possibility is to lower the temperature, and this will indeed work, but it may then require a very large reactor to get conversion because the rate will slow down. The other is to take advantage of membranes and selectively remove a product. So for example, if we could selectively remove product C as it forms, then more in A and B would react together to make more C and D to approach equilibrium. And so if we can find a membrane that is selective, then we have the potential to shift the equilibrium to the right and keeping the temperature high, so keeping the rate of reaction high. So here is a schematic representation of a membrane reactor. We're feeding our reactants, A and B, so F is a molar flow rate of A and B into the reactor. We're assuming for now it's an ideal membrane. Only C goes through the membrane. So the membrane is here, and we have C going through, and then C is leaving this direction. Leaving the reactor is A, B, product C that didn't go through the membrane, and product D. Of course, we have to have some C leaving or we wouldn't have a driving force for C to go through the membrane. And the idea is if we look at, say, the rate of formation of product D, well, it'll be a rate constant for the forward reaction, say concentration of A, concentration of B, for example. Rate constant for reverse reaction, concentration C, concentration of D. And what we're doing is decreasing the concentration of C by using the membrane reactor. In this case, I've represented it as the membrane is also a catalyst, since most reactions are catalytic. So catalytic reaction takes place in this porous membrane, and we preferentially or exclusively remove C. In a real membrane, typically we also are going to remove some A and B and D, and we need a good enough membrane to selectively remove C to make it economical. The other way we could envision a membrane reactor is to fill a membrane with a catalyst, and so the catalyst causes the reaction. The membrane is catalytically inert, but is preferential for one of the products. So here shown a representation of this where we're flowing, for example, let's look at a simpler reaction, A reacting to B plus C. And so flow rate of A, molar flow rate enters, leaves A and B and C, and then through the membrane wall, which is here, would be, for example, C diffusing through, and the diffusion permeation would take place because of a pressure difference or concentration difference. In other words, we need the concentration of C on the reactor side to be higher than the concentration of C on what is referred to as the permeate side. We have to have a driving force for that permeation take place. Strictly speaking, it's a chemical potential. We'll look at it here in terms of concentration. So again, we're assuming an ideal reactor. So now if we write down the mass balances for this reaction, assuming it's plug flow inside the packed bed. So the change in the molar flow rate of A, that's FA, respect to cumulative volume, It's going to be rate of reaction. The rate of reaction may be minus K Ca plus, so K forward, K reverse, Cb, Cc. For B, we have the exact same type, except this would be minus R sub A. And what's different is when we write the balance for C, we have minus R sub A again, and then we have an additional term which represents the flux through the membrane times the area for permeation per volume. And D is the diameter of the tube, the inside diameter, pi times D times dz. So dz, some differential distance where z is distance down the reactor per differential volume. And we can, of course, reduce this minus R sub A. This differential volume would be pi d squared over 4. That's cross-sectional area times dz. So that this just reduces to 4 over d. The only thing we need is the flux of C, which would be the permeance of C times the concentration of C in the reactor minus the concentration of C on the permeate side. So this concentration, of course, is the same concentration that's in the reactor that affects the rate of reaction. This is on the permeate side. We need a driving force. Typically, we're going to have, of course, a higher pressure inside the reactor to make the membrane reactor work. And the other thing we have to keep in mind is our total molar flow rate is going to change. Now, in this case, we have 1 mole going to 2. If this were a gas phase reaction, the molar flow rate would increase, which affects the concentrations. Now we're going to be removing C through the membrane, so we have to take that into account when we calculate the total molar flow rate. Now we can solve these differential equations same way we would for other plug flow reactors, as long as we have a value for the permeance. So this is the permeance, which is a property of the membrane.